Hello everyone, I'm Nitin. I'm a PhD student in computer science at the University of Oxford. I will be talking about design and governance challenges for privacy-preserving computation. This work was a collaboration between Oxford CS and Microsoft Research, and my PhD is supported by CallSign. While data sharing has opened up unprecedented opportunities for better living and powered the digital economy, it has become clear that widespread data sharing also creates unprecedented privacy risks that can pose significant harms. To try to reduce such harms, both technical and legal regulatory methods have been devised. With respect to technical methods, a new class of algorithms, broadly considered methods for privacy-preserving computation or PPC, have emerged over the last few years that enable data to be computed upon while providing robust theoretical privacy guarantees about what can be inferred during and as a result of computation. However, there's been a very limited uptake for these technologies in the real world. We want to better understand why this is the case, better understand the opportunities and barriers presented by these technologies. This research is about understanding the challenges to adoption of privacy-preserving computation, getting a clear idea of just why people are motivated to use these rather complex computational methods. We then dig deeper on how these methods can be explained, governed, and made accountable. Since we wanted to explore how PPC are being socio-technically constructed and get a much broader appreciation of challenges PPCs present, we chose to undertake in-depth semi-structured interviews with PPC experts from a range of backgrounds and roles, including researchers, policymakers, social designers, and industry practitioners. We deliberately selected some experts who were boundary workers and knowledge brokers who bridged between the domains of science, industry, and the government. This study focused on three most promising PPC primitives: multi-party computation, which enables secure evaluation of a function over data shared across multiple parties; homomorphic encryption, that enables computation over encrypted data without ever seeing the input or the output through a specialized encryption and decryption scheme; and differential privacy, which is a framework for sharing information based on a dataset while statistically limiting the information exposure about the individual in the dataset. We performed the thematic analysis of the interviews and identified two main themes with three sub-themes each. Many participants noted that advances in the theory underpinning privacy-preserving computation techniques do not always translate straightforwardly into specific real-world applications. In some cases, this was because the scientific work made simplifying assumptions that were rarely satisfied in real use cases. Several participants discussed the overarching need for people with different skills, backgrounds, and motivations to work together. A common theme among both researchers and industry practitioners was the complexity of applying PPCs from a software engineering perspective. Participants articulated this as a trade-off between approaches to building PPCTs that either work out of the box but have poor and unpredictable performance, or that have reasonable performance but require fine-tuning by an engineer. Unsurprisingly, privacy was often cited as the main motivation. Some cited the existence of privacy and data protection regulation as an incentive to provide and deploy PPCs. Our participants discussed the aspects of explaining privacy-preserving computation, including how they go about explaining PPCs to different audiences. Several participants also cautioned that the kind of explanations offered need to be tailored to the audience. On one hand, explanation could be too technical. On the other hand, short intuitive explanations might be too simplistic for informing executive decisions. It was seen as sufficient that end users trust the provider of the solution that they do a good job. A final theme concerned the challenges of governance and accountability of privacy-preserving computation. Even if explanations are not able to provide an individual with a complete technical understanding, it might still be possible to outline and justify them to a wider public. Participants also proposed that certification credentials and trust marks applied to services which use these techniques could help individuals to seek out more trustworthy systems. Before I end, I would like to conclude with some key takeaways from this study. PPC technologies and the values they embed are shaped by their creators and the broader political, economic, and regulatory forces around them. For PPCs, there are limits to abstraction. If we try to hide technical details behind APIs, we may lose the ability to adapt these technologies to particular contexts. PPCs can seem mysterious and even magical. However, they should not take away the need to make these systems accountable to affected stakeholders and the wider society. PPCs formalize privacy as confidentiality, but this is not the only way to understand privacy. And even if they protect privacy, they may still enable panoptic surveillance, which can reinforce problematic power relations in a digitally enabled society. I hope you enjoy reading the paper. Thanks for watching.